Welcome back to the deep dive. So last time we dug into the era of experience, right?
Yeah, that whole fascinating question about AI's future training data.
Exactly. What happens when it's basically read, well, everything humans have ever written?
Where does it go next?
And today we're sort of picking up that thread, looking at a potential answer. AI learning from its own experiences.
And we've got a really concrete example to explore. Mobility AI.
Right, mobility AI.
Right.
We're going to analyze this to see how AI interacting with the real world might be, well, a step towards AGI, artificial general intelligence.
Precisely. We'll be looking at a Google research blog post about mobility AI from April 2025.
Okay.
And we'll also connect it back to some of David Silver's ideas from DeepMind about this whole era of experience concept we discussed before.
Got it. So the mission for you listening is to see a practical example of AI moving beyond just human data.
And to grasp the implications for AI's future, how it might solve really complex real-world problems.
Okay, so let's just quickly recap that core idea from the era of experience. David Silver's point basically was that relying only on human data, it has limits, right?
It definitely has limits. You eventually hit a ceiling defined by the scope and, frankly, the biases and limitations of human knowledge. AI needs to generate its own data through experience to surpass that.
And mobility AI is a prime example of this.
Yeah.
Even though humans built it initially.
Exactly. Its whole design revolves around learning and improving by, directly interacting with the complexity of urban mobility.
The messy reality of traffic and people moving around.
That's it. It's not just analyzing reports, it's digitally experiencing the flow of the city.
Okay. And Google structures this around 3 pillars: measurement, simulation, and optimization. Let's start with measurement.
Yeah, measurement is foundational. It's all about getting a really deep understanding of how things currently work.
How we're all getting around, basically. So how does AI help with that?
Well, it uses machine learning on loads of data, real-time and historical. One cool example is these congestion functions they're developing.
Okay, congestion functions. How do they work?
Instead of older, simpler traffic models, these use ML on data from connected cars, anonymized speed data, that kind of thing.
Okay.
To build these really detailed city-wide maps of how congestion forms and spreads.
So it's more dynamic than just seeing a red line on a map.
Much more. And what's really interesting is these models can show how subtle changes, like adjusting traffic light timings, can impact flow across the whole city. It's like the AI is learning the city's pulse.
That is a deeper level of understanding. Identifying causes, not just symptoms. You also mentioned foundational geospatial understanding.
Yes. This uses something called self-supervised learning. The AI looks at geospatial data, movement patterns, and it learns the underlying relationships between places. It creates these things called embeddings.
Embeddings, like digital fingerprints for locations.
Sort of, yeah. They capture not just where a place is, but how people move around it, the typical patterns. Really useful where traditional data is thin.
And they're even using generative AI for this now.
They're collaborating with Google Research on that, yeah.
To
boost that spatial reasoning aspect. It's about building this incredibly rich, dynamic picture.
Makes sense. And it's not just cars, right? You mentioned parking. Always a headache.
Definitely not just cars. Parking's a big piece. Using ML to manage parking better for everyone, drivers, deliveries, even future autonomous vehicles. Smoothing out that whole process.
Okay. And then the big one. Where are people actually going? Origin destination.
The OD matrix. Yeah, crucial. Knowing where trips start and end is fundamental for planning. Where are the strains? Where do you need better transit?
Right.
Mobility AI calibrates these OD matrices using observed traffic, making them reflect reality much better. It gives planners a really solid base.
So it's like assembling this giant, constantly updating jigsaw puzzle of city movement.
That's a good way to put it.
And a key part must be figuring out if the changes they suggest actually do anything, measuring the impact.
Absolutely critical. They use aggregated, anonymized Google Maps data for that. See how interventions affect congestion, travel times.
Okay.
And they have other metrics too, like analyzing hard-braking events, HBEs, as a proactive safety indicator, spotting risky areas before crashes happen.
That's clever, using braking data for safety.
Yeah. And maybe one of the most impressive bits is their work with NREL, the National Renewable Energy Lab.
Oh, yeah. What's that?
They built AI models to predict vehicle energy consumption on different routes. This powers the fuel-efficient routing you see in Google Maps.
And that actually saves fuel.
Big time. They estimate it's avoided almost 3 million metric tons of CO2 emissions just in the U.S.
Wow. That's a massive real-world impact, directly from understanding and optimizing the system.
It really is. And they even use advanced stats, like synthetic controls, when they can't run, a perfect experiment.
Like for policy changes.
Exactly. Like analyzing NYC's congestion pricing, they create a statistical twin city using historical data to compare against. It helps isolate the policy's true effect.
Okay, that's measurement covered. Really detailed understanding. Pillar 2 is simulation.
Right. Simulation. This is about building, essentially, digital twin...
Virtual copies of the transport network.
high-resolution copies of the entire system, not just a few streets.
The whole city.
Whole metropolitan areas. This lets planners test interventions virtually, traffic signal changes, new roads, even emergency evacuation plans.
Like a giant transport sim city, but based on real data.
Kind of, yeah.
Yeah.
You can experiment without causing real-world disruption or spending millions up front.
That sounds incredibly useful, but computationally must be immense, simulating a whole city's traffic.
Oh, it's a huge challenge. Traditionally, simulations were very localized. Scaling them up to thousands of road segments was a major research focus.
How do they manage that?
A big part was improving the calibration, making sure the simulation actually behaves like the real world.
Right, getting the parameters just right.
Exactly. They feed it much richer data. Now aggregated speeds, travel times, counts into what they call physics-informed models.
Physics-informed. So it knows how traffic actually flows.
Yeah, it combines data patterns with known traffic dynamics. They're also working hard on making the calibration process faster, more efficient.
So it's not static, it's learning and adapting the simulation itself.
Precisely. And it's not just about predicting one outcome. They're also building ways to quantify uncertainty.
Uncertainty. Like what if demand changes unexpectedly?
Exactly that. Or road closures, accidents. It allows for more robust what-if analysis, showing a range of possible outcomes, not just a single prediction.
That makes sense. Gives planners a better feel for the risks. Okay, so measurement simulation brings us to pillar 3, optimization.
Optimization. This is where they take all the insights from the first two pillars
The understanding and the predictive power.
and apply advanced algorithms, AI, to actually design and implement better transport solutions, putting the knowledge into action.
Okay, give us some examples. What does this look like on the ground?
Well, one area is intervention design. They worked with Seattle DOT, for instance, on managing traffic after big events much more effectively, and evacuation plans for places like Mill Valley in California, figuring out network tweaks to get people out faster in emergencies.
That's critical stuff.
Definitely. It also applies to managing traffic around work zones better or optimizing freight movement and developing routing strategies that don't just have one driver but improve efficiency for the whole network.
Reducing those social costs like wasted time and emissions.
Exactly. And Project Greenlight is another classic example, using AI to optimize traffic signal timings.
Reducing stops, saving fuel, cutting emissions.
Yep. All comes under optimization.
It's really powerful seeing how those 3 pillars work together. Measurement, feeding, simulation, both informing optimization.
It's a continuous loop, really.
Okay, now let's loop back ourselves to the era of experience and that link to AGI. How does mobility AI really embody what David Silver was talking about?
Right. This is where it gets really interesting from an AGI perspective.
Okay.
Think about how mobility AI learns.
Okay.
Through its constant measurement of the real-world traffic congestion, the results of changes it makes, it's generating its own experience, its own data stream.
It's not just crunching human-made data sets. It's observing reality directly.
Exactly. It's building its models based on its ongoing interaction with the world. That's a fundamental shift. It's learning the dynamics of the system.
Like a scientist running continuous experiments.
In a way, yes. And look at the feedback loops. They tweak a signal timing. Mobility AI measures the impact, less congestion, maybe more hard braking, lower emissions. That's direct feedback. It strongly mirrors reinforcement learning, right? Agent takes action, gets reward or penalty based on outcome.
So kind of like AlphaZero Learning Go. It plays, it sees if it won or lost, it adjusts. Mobility AI makes a change, sees the impact on traffic metrics, adjusts.
It's a really good analogy. AlphaZero Learn Go from self-play. Mobility AI in this vastly more complex, messy, real-world domain.
Yeah, much messier than Go.
It's also learning by doing. It refines its understanding, its strategies based on the experiences it accumulates from interacting with the city.
But the reward isn't as simple as win-loss. Urban transport has multiple goals, sometimes competing ones, right? Less congestion might conflict with something else.
That's a key point. Unlike Go's single objective, mobility AI optimizes across multiple metrics simultaneously. congestion, safety via HBEs, emissions.
Right.
It's learning to balance these complex trade-offs based on the signals it receives from the environment. This fits Silver's idea that real-world intelligence needs to handle numerous, often noisy feedback signals.
So the measurement part is the AI observing its world. Simulation is like testing hypotheses. Optimization is acting on what it's learned.
That's a great way to frame it. The goals might be set by humans initially improve transport, reduce emissions, but the how is increasingly learned by the AI through its own experience.
It's not just following rules we wrote based on old data.
Precisely. And its ability to model and optimize something as incredibly complex as urban transportation, that feels like a genuine step towards the kind of broad adaptability and problem solving we expect from AGI.
It shows AI learning from the world, not just about it from our descriptions.
Exactly. It's engaging directly.
Okay, let's wrap up this deep dive then. Mobility AI really does seem like a fantastic illustration of this shift into the era of experience.
It absolutely is. That framework, measure, simulate, optimize. It's a perfect blueprint for how AI can learn from its own real-world interactions.
This idea of experiential learning.
Yeah, and it's not just about fixing traffic jams. It points towards a pathway for AI to tackle other complex challenges, potentially leading to more general intelligence by learning how the world works through active engagement.
Okay, so here's something to leave you with, a final thought. If AI, like mobility AI, can learn to improve systems this complex through its own interactions, what other domains are out there?
Where else could this apply?
Think about it. Climate modeling, economic systems, healthcare logistics. What happens when AI starts learning directly from those complex realities?
What unexpected capabilities might emerge?
Exactly. As AI gets better at learning from the world itself, not just from our data about it, could we see those unpredictable leaps, those Move 37 moments, happening in all sorts of critical real-world fields?
It's a really powerful question. What happens when AI truly starts learning by doing everywhere?
Definitely something to think about. Thanks for joining us for this deep dive.